So what I have here on my doc cam, this is a vector field. This was drawn for an old recitation quiz from a previous semester. I thought it'd be nice though to illustrate that same sort of principle that Clinton was talking about in the handout there. So what we have is a vector field, and in this vector field, the lengths of the vectors has actually been drawn in. You can see that there are some vectors that are actually 0 toward the center, and then we have vectors of larger magnitudes sort of in the corners here. And in this vector field, we have 4 different paths. We have A, D, C, and D. And what we want to do, or what I'd like us to do, is to briefly consider whether the line integral, that's going to be the summed effect of these vectors along the path, is going to be positive or negative. And we'll just take them one at a time. So taking a look at path A, notice that path A, at pretty much every point that we encounter a vector in the vector field, the path is orthogonal to the vectors, right? And that means that those vectors will neither have an additive nor a subtractive effect if we're to take their weighted sum along this path. And so the line integral, right, through this vector field along the path A would be very close to 0. We don't know it's exactly 0, but we can deduce that it would be very close to 0 because those vectors are all orthogonal to the path. Along path B, okay, well, the vectors are very close to 0 at the beginning of the path. And then as we get closer to the terminus here, we notice that the vectors are making an acute angle, right, with our path here. That is to say, if we're thinking of this as wind, it's a tailwind, right? It's pushing us along. And so our line integral along B, although we don't know what the value is, we can deduce that it would be positive because the vectors are mostly pointing in the direction. In fact, I can't really find any except maybe at the very beginning, very small vectors that would be pointing opposite the direction of travel. So the positive line integral along path B. And path C, now path C, we can see we're moving against the vector field really for the entire path. So the line integral along C would be negative. And then D is an interesting one. So D, again, we have a lot of vectors that are close to being orthogonal that won't really affect it much. But do notice that every time we encounter a vector, it does look like it's just barely an acute angle. These vectors are pointing in the direction of travel more than they're pointing away from the direction of travel. And so the line integral along D should also be positive, although it's also probably not very much compared to the line integral along B, for example. Okay, so just a little bit of a graphical introduction to vector fields here. You know, the book's organization jumps around a little bit in this chapter. We start by talking about vector fields in general and what a conservative vector field might be. We come back to that in section 16.3, where we have some very specific tools for looking at various integrals and conservative vector fields. And then 16.1, 16.2 has to do with these line integrals and some techniques for calculating them. So I wanted to start with this. I'm also going to jump around a little bit in the recitation examples. I actually want to look at problem 3 before we get to calculating some line integrals here. So problem 3 asks us about a couple specific vector fields. So this one is given by, in 2 dimensions, by the way, by 3x squared plus 2y right in the x direction and 2x minus 2y in the y direction. And the question is this a conservative vector field? It turns out a little bit later in the chapter that when we have conservative vector fields, we have some really convenient calculations that we can make on those that save a lot of time and effort. So it's nice to know that. If you're sort of wondering, like, why do we care if they're conservative or not, that's a good thing for a little later in the chapter. But let's see if we can figure out whether the 2 vector fields given here are conservative. So they ask if it's conservative. The easiest way to know if a vector field is conservative is to ask whether those vectors, right, or whether f here could be the gradient of some other function. If we could identify a function whose gradient is exactly this, then we will have shown that the vector field is conservative. If we can show that no function could have a gradient equal to this vector, then we've shown that it's not conservative. As it turns out, it's typically easier to show that a vector field is not conservative because all we need is a single counter example to this general principle about our cross partial derivatives here. So like if this were to be the gradient of some function, here's what would have to be true in 2 dimensions. If we think of this as here's f1 and here's f2, right? Those are the components in the x and the y direction. If it's conservative, then this would have to be true. The partial of f1 with respect to y would be equal to the partial of f2 with respect to x. We want to know, is that true? Well, this particular function, you might actually be able to just sort of guess or imagine a function that's going to work. I want to show you a little bit of more of a systematic way in case you encounter a problem that it's not really clear, like, is there such a function or not? So what we're going to do is we're going to actually take some antiderivatives here. So let's take a look first at f1. All right, so f1 is our first component here, and if we were to take antiderivatives of the various parts here, can we construct a function that's going to work here? So let's do the following. Let's take our antiderivative of 3x squared plus 2y. Okay, so there's our 3x squared plus 2y dx. What would that antiderivative be? So let's see, what would that be? That would be x cubed plus 2xy, and then plus like some constant, but really plus some function of y. Right, so there's our antiderivative one component here. Let's now consider the following here. So if we took antiderivatives of both components here, like could we construct some function that's going to give the same result here? So is there some function whose antiderivative with respect to y and with respect to x of the two components here will be equivalent? So let's see, let's consider that. So here's this function. This could be anything, right? And then if we take an antiderivative of our other component as well, so 2x minus 2y. Okay, so if we allow that to take the antiderivative with respect to y, we get, let's see, we get 2xy minus y squared plus some function of x. Okay, so let's compare those two here. So could we choose g and h to make these two things equivalent, right? Could we make some choice of functions here that make these be the same thing? All right, so what do we have in common here? We have this 2xy and our 2xy. Could we let h of x be x cubed and g of y equal y squared? Let's see if that gives us what we want here. So if we let g of y equal y squared, h of x equal x cubed, then we would have the following function of f of x comma y equals x cubed plus 2xy plus y squared. Well, okay, let's see if this passed the test. Could this be the function whose gradient is equal to the vector that we've been given? Well, what's our partial with respect to x? Partial with respect to x would be 3x squared plus 2y, 3x squared, 3x squared plus 2y, and our partial with respect to x. Okay, so that would be, with respect to y, would be 0 plus 2x, and then, that's a minus there, so minus 2y. And if you see what we came up with, so yeah, we actually have found a function now whose gradient is exactly equal to the vector field that we found here. So in general, what this technique is here is that we integrate with respect to our two variables here, right? And typically we'd have this be a constant, but since we're taking partial derivatives, our antiderivative could be a constant or really a function of the opposite variable. And by simply choosing g and h to be the missing parts between these two functions, we can construct an original function here. This is our potential function, x cubed plus 2xy minus y squared, that gives our vector field, or at least whose gradient is equal to this vector field. Okay, so there's a little bit of guess and check here, or a little bit of trying to engineer an equation that's going to give us the things that we want. If we have time at the end, I might come back to another example. I'd like to take a look at problem B here. So problem B gives us a vector field in 3 dimensions: x squared plus z minus y, y squared plus x minus z, and z squared plus y minus x. And there's a nice sort of symmetry to this vector field here that makes us perhaps think that it is a conservative vector field. Now, earlier I mentioned that's actually, in general, easier to prove that a vector field is not conservative. For a vector field to be conservative, the curl has to be equal to 0. The calculation of the curl is given in 16.1. The curl is given by a 3 by 3 determinant. But really what we want to see here, or simplification, especially if we suspect that it's not conservative, is to check the cross-partial derivatives. So what I mean by the cross-partial derivatives is, okay, so we have f1, we have f2, and we have f3. And so the partial of f1 with respect to y has to equal the partial of f2 with respect to x. Right, so in other words, that's the x component of the vector field differentiated, partial differentiation with respect to y, and the y component we differentiate partially with respect to x and compare those two things. They have to be equal. Okay, so the z component partial derivative with respect to y has to equal the y component partial derivative with respect to z. Right, so really what we're doing is we're swapping the components with what partial derivative operator we're applying to them. And we have to compare all the different pairs here. So x and y and z, z and x. That makes 3 pairs of cross-partial derivatives. If even one of those pairs is not equal to 0, we can show that the curl is non-zero and the vector field is not conservative. So one thing that we might do if we're trying to disprove is we might just try and take a look at these various components here and see if we can detect where taking partials might result in different pieces here. So here's one thing that I notice. I notice this negative x in the z component, and I notice this positive z in the x component, and that makes me suspect that maybe taking the partial of f1 with respect to z and comparing it to the partial of f3 with respect to x, maybe that's where we can engineer a counterexample and show that this vector field is not conservative. So let's just do that quickly. So f1, if we take a partial with respect to z, the x squared and the minus y are treated as constants, and our partial derivative is just 1. If I take a partial of f3 over here with respect to x, the z squared and the y are 0, and negative x, well, that will give us negative 1. So that right there is a counterexample, right? That single counterexample tells us that this is not a conservative vector field. Now, right, I've taught calculus before. I've seen a lot of examples, so it was easier for me to sort of identify which cross partial was going to give us the counterexample. You should be prepared to try a bunch and perhaps even all of our cross partial derivatives to compare them before you discover such a counterexample. So just not to cheat you out of some of that hard work, if I did this calculation, for example, if I took f1, and let's see what we want to do here. I want to take, let's do f2 partial with respect to x. And let's see, let's do, actually that gives us a counterexample as well. I'll find one that actually works. How about f1 with respect to y? Actually, we're going to find a bunch of counterexamples here. I think the only one that we can maybe engineer to be the same, yeah, z and y. Yeah, we're going to have a lot of counterexamples here. Okay, good. So I think they gave you a problem here where if you go searching for cross partials, you're going to come up with quite a few counterexamples. Problem's over as soon as we find one of them, right? If we find one cross partial that's not equal. All right, so that's quite a bit about vector fields. It's more important in 16.3, I think, and 16.4, but it's nice to introduce these things now. What I want to do next is take a look at a couple line integral problems. Just want to pause for the folks who are viewing live and see if there's any questions. I see a question here. Where did the g of y come from? Okay, that was a few moments ago. I think that is back here in problem 1. Okay, so the g of y. So when I took this antiderivative with respect to x, right? So remember, these are partial derivatives, right? Partial derivatives would be the opposite direction here. It's possible that we have some function of y, that is, g of y could be a constant, or g of y could have some collection of y's, y to the 5th, y to the 10th. Regardless of what g of y is, if we were to take the partial derivative of this answer with respect to x, all those y's and all those constants would head to 0. Okay, cool, good. Sounds like that was answered already. Same thing with h of x. So h of x could be a constant. H of x could contain a function of x. The important thing is that h of x doesn't contain any y's and g of y doesn't contain any x's there. So all I'm doing is I'm representing a family of antiderivatives here that might contain constants and might contain functions of the opposite variable. So I also know that the activities that are leading up in, I think, 16.3 will give us a little bit more practice with these vector fields. Okay, so can I explain what a line integral is? Yeah, and so at the beginning of the session here, I gave a metaphor. Actually, I gave Clinton's metaphor about riding a bike and thinking of a vector field as giving like the wind in a windy place like Livingston, where sometimes the wind pushes for you and sometimes against you. In that metaphor, the line integral along a path was the net effect of the wind on your velocity as you take that bike ride. So that's a really applied example. I want to see if I can give a more generalized example of what a line integral is. So a line integral, first of all, is a path through some vector field, right? So there are vectors at every single point on that path that we encounter, some that work in the direction of travel, some that work against the direction of travel, some of which are neutral. Those would be orthogonal to the direction of travel. The line integral is the weighted sum of the effect of all those vectors on that path through the vector field. All right, so I think that's a very generalized answer, and it might be unsatisfying in some senses. I think it's like, keep both things in mind. Keep that applied example of riding the bike, and keep the most general idea with you as well, okay? So I guess maybe one more reminder that all integrals are essentially Riemann sums, right? We're adding up a bunch of things. We're adding up an infinite collection of things. And in this case, the things are those weighted effects of the vectors in the vector field relative to our path. Okay, so let's do some examples too, and it might be helpful, or it might help your general understanding too, to just see like how we go about calculating these things. So problem 1, we have a line integral, right? C is our path. In this case, it's a straight line segment. And this is what we're integrating, x e to the y. And we're integrating from 1, 0, 2 to 2, 2, 3. One of the main techniques that we're going to use in this section for evaluating line integrals is to actually turn them into single variable calculus problems using parametric equations. Excuse me. So all that work we did earlier on in the semester using parametric equation of a line, those are going to come back and help us in this section here. So we need a few things here. So I want to draw your attention to a couple pieces here. First is this ds. Okay, so ds, it's like an arc length integral, and we can write that in a couple different ways. We're in 2 dimensions, or sorry, we're in 3 dimensions here. So we can write this in a couple ways. One, if you remember back to arc length from like Calc 2, we could think of it in terms of the following, right? So the square root of x prime of t plus y prime of t plus z prime of t, right, dt, would be one way that we could think about that. The other way that we're going to do it, and here's how we're actually going to do it in the problem here, if we have some parametric equation for our line here, the other way that we could think about this, rather than using x, y, and z, is if we have some sort of parametric equation r of t, well then what we can do is take the magnitude of r prime of t, right? And that's just the calculation that we'd have right here anyway, times dt. So what we're looking for is a parametric, parameterization of this straight line, that'd be r of t. We're going to rewrite the entire problem in terms of that parameter t, and turn it into a single variable calculus problem. So let's start by just considering this line going from 1, 0, 2 to 2, 2, 3. Let's see, what would our parametric equation be? Well, what's our change in x going from 1 to 2? That's 1. Okay, so if we start at the point 1, 0, 2, and then we add 1 to x, we go from 0 to 2 on y, so 2 for y and 3 for z if we go from 2 to 5. There's our parametric equation for this line. So that's our r of t, right? That's a parameterization of the line. So what we're saying then is let's let x equal 1 plus t, let's let y equal 0 plus 2t, and let's let z equal 2 plus 3t. Okay, so we have the line written in terms of t, and we're going to take our function x e to the y and also translate that into a parametric equation using the same parameterizations. Let me just write those down just so they're a little bit easier for us to see here. So we have x equals 1 plus t, y equals 0 plus 2t, and z equals 2 plus 3t. So what we're going to do, we're going to rewrite this integral strictly in terms of t. Oh, sorry, one more important thing. So to traverse the straight line segment from 1, 0, 2 to 2, 2, 3, we also have to consider what values of t would accomplish that. And what you know from writing these parametric equations for lines is we can choose, there's actually a lot of parametric equations we can choose. The easiest one is to let our points traverse from point 1 to point 2 over the course of 1 unit of t. That is from t equals 0 to t equals 1. If we plug in t equals 0, we get the first point. Plug in t equals 1, we get the second point. And so that's going to give us a domain for t. So t is going to range from 0 to 1. So let's write our integral now. So our integral over that path of x e to the y ds is equal to the integral from, I'll just write this in general first, so from t1 to t2 of, right, so if that's our function, that's our original function there, we're going to rewrite that in terms of t. So what's x? X is 1 plus t, so 1 plus t. E to the y, that would be e to the 2t. Okay, so there I've rewritten x e to the y. I also have to write ds. So ds is equivalent to the magnitude of r prime times dt. So let's just do that as a side calculation over here. So I have that r of t equals, we have 1 plus t, we have 0 plus 2t, and we have 2 plus 3t. And so then r prime of t would be just 1, 2, 3. And then the magnitude of r prime would be the square root of 1 squared plus 2 squared plus 3 squared, which is root 14. Okay, so the last part here, I'm going to rewrite ds. ds is equal to the magnitude of r prime times dt. So let me do the following. Let me put the dt inside the integral. Let me put the magnitude of r prime. I'm just going to put that outside the integral by the constant multiple rule. I don't really need a root 14 hanging around inside my integral. So I'm going to solve this with you guys, but if you just take a minute to just like zoom out, look at it, like, aha, that's a single variable calculus integral. We should be able to solve it. 1 plus t and e to the 2t. We can do integration by parts to solve this. Right? And finally, I guess I could just change this right now. T is going to range from 0 to 1 in this problem. That's how much time it takes to go from the first point to the second point. I'm just going to pause here before we go into evaluating the integral, see if there's any questions about the setup there. Again, the general strategy is to take this line integral of several variables, use parametric equations to turn it into an integral of a single variable. Okay, I'm going to keep solving this. If you guys have questions, maybe type them in the chat, and I'll try and address those after we're done with the integral here. All right, so let's see. We have a 1 plus t. We have an e to the 2t. This looks like a good candidate for integration by parts. Let's do the following. Let's let 1 plus t, we can let that be u, and we can let e to the 2t dt, and let that be dv. If we make those choices, then du would just equal dt, and v would be 1/2 e to the 2t. Let's just check, make sure that's right. 1/2 e to the 2t, its derivative would be e to the 2t. All right, everything looks good here. And so then our integral right here, we're trying to solve, still got that root 14. And integration by parts, let's see, we're going to have u times v, right? So u times v, so that gives us 1 plus t, there's u, and multiply that by 1/2 e to the 2t. And again, evaluate that at the endpoints of 0 and 1, and then subtract the integral of v du. So minus the integral from 0 to 1 of 1/2 e to the 2t dt. Okay, and let's see. Let's go piece by piece here. If I plug in my endpoints here, 1, I'd have 2 times 1/2 e squared. So 2 times 1/2 e squared, that would just be e squared. So I have e squared minus our endpoint at 0. If we plug in t equals 0, we get 1 times 1/2 e to the 0. So 1 times 1/2. So I get e squared minus 1/2, I believe. Let's try that. E squared minus 1/2. Yep. And then we're going to subtract the following integral here. So we'll take an antiderivative. That should be 1/4 e to the 2t. Again, evaluate that one at 0 and 1. And so we have root 14 times, let's see, e squared minus 1/2. And if we evaluate this, the endpoints of 1 and 0, the endpoint of 1, we have 1/4 e squared. And then we're going to subtract our endpoint at 0, so minus negative give us plus 1/4 e to the 0. Okay, so I have some like terms here. I have e squared minus 1/4 e squared. So that gives us e squared minus 1/4 e squared is 3/4 e squared. And we have a minus 1/2 plus 1/4. Combine those into a minus 1/4. And this is about as simple as this answer will get. We'll just leave it like that. So the end of these problems, the beginning of these problems is just using parametric equations to try to turn it into a problem of a single variable. Second part of the question is using some of those sort of intermediate integration techniques depending on the integral. So I'm going to pause before we go on to problem 2. Problem 2 is pretty similar in terms of our calculation. We're going to do a similar parameterization. Okay. So again, if you have questions, we should have some time at the end. I can come back to any of these problems if you'd like to see them in more detail. Okay, so problem 2 here. Problem 2 gives us, right, our function f of x, y, z is x, xz, x squared. C is the segment of a helix. Ooh, okay, so now we have a path that's not a line. following r of t equals cosine t, comma 2t, comma sine t. We're going to trace this out from t equals 0 to t equals pi over 2. Okay, so graphically, what's going on here? Well, we're following this helix path in 3 dimensions, and we're integrating this function at every point along that path. Right, that's the idea here of this line, this path integral. All right, well, so how are we going to do this in general? So generally, we already have a parameterization, right, for r of t. So we're going to try and rewrite f in terms of that parameterization, and rewrite dr in terms of t, and see if we can turn this into a single variable calculus problem just in terms of t. So what do we have here? Okay, so we have r of t is cosine t, 2t, sine t. And so I'm just going to copy that here. So we have r of t is the vector cosine t, 2t, sine t. And we're going to need this. We're going to need r prime of t. So r prime of t is negative sine t, comma 2, comma cosine t. And here's the general identity that we're going to use for this one here. We want to take this line integral over the path c of f dr. What we're going to do then is take our integral again from t1 to t2, right? That's our parameter t. And we're going to rewrite f as a composite function. So f of some parameterization of x, y, and z. And then dot that with r prime times dr. And just as a quick explanation why we're going to do this part here, if we think about r prime, one way we could write that is, right, dr dt. I have a small mistake here. That should be dt right here. Okay, so r prime of t is dr dt. And if we multiply dr dt times dt, that gives us the derivative of r. That gives us our dr that we have in the original here. So just a quick derivation, like where this term comes from. It's basically a chain rule problem. We're rewriting x, y, and z in terms of t. And so to do so, we multiply by r prime, right? And r prime times dt gives us that dr anyway. All these formulas are in section 16.2. Again, they spend a lot of time working on integrals that are following a linear path before going on to a more generalized path. Remember, all the techniques that we use here would also work for a problem where the path of the line integral is actually linear. Okay, so let's take a look at these parts here. So we're going to need the following. So we have r of t. So we're gonna rewrite f in terms of that variable t. So rewrite x, xz, and x squared using this parameterization. We have r prime. That is a dot, by the way. This is a vector valued function. That is a dot product there. And see if we can rewrite this strictly in terms of t. And then we're off to the trigonometry races after that. All right, so go piece by piece. We're going to span from 0 to pi over 2, right? Those are our endpoints for t that are given to us in the problem. F of r of t. Okay, so we're going to rewrite the function f in terms of t. So that's still a vector. First component is x, which we're going to rewrite as cosine t. Second component is x times z. So x times z would be cosine times sine. So cosine t, sine t. And our z component is given by x squared, so cosine squared t. Okay, so there's our f of r of t. We're going to dot that with r prime of t. So dot that with the derivative of r prime. So dot that with negative sine t, comma 2, comma cosine t, all times dt. Okay, so I'll calculate this dot product here. So what do we have? We have a cosine times a negative sine. So we have negative sine t cosine t. Add that to 2, right? So 2 times cosine t sine t. Right, that's the middle component of our dot product. So 2 sine t cosine t. And last component would be cosine squared times cosine. So we have a cosine cubed t dt. So again, before we dive into sort of the tough work of evaluating this integral, we should just like zoom out for a minute and say, aha, I've turned my multivariable calculus problem into a single variable calculus problem. Give myself a pat on the back. Even if that integral is going to be a little bit challenging to calculate, we've accomplished the hardest task, which is turning it just into a single variable calculus problem. Okay, so let's see, what do I have here? I have a 2 sine t cosine t, I have a minus sine t cosine t. That's nice, those will cancel. So let me just write a simplified version here, going from 0 to pi over 2. And what I really have is, let's see, so cosine cubed t plus sine t cosine t dt. So there's a variety of ways that I could solve this. Excuse me, just need to blow my nose here. Don't worry, I don't have the virus as far as I know. I do have a little bit of a stuffy nose though. Okay, so the key is going to show you a little bit of a longer way to deal with this integral here. I'm gonna like do more trig and less calculus. That's just my personal bias in problems like this. I see sines and cosines. Sines and cosines play nicely together. So here's how I'm going to go about doing this. Let's factor out a cosine. So let's factor out cosine t from both terms here. So that leaves us with cosine squared t plus sine t dt. And now if I use a Pythagorean identity on cosine squared, I can rewrite this as a whole bunch of sines, right? Sine squareds and ones and things like that times cosine. And that sets me up for a pretty simple u substitution. The alternative, there's a lot of ways you could do this. You could do 2 different integrals with u substitutions. I think there's probably a way to do it using integration by parts as well. I think this is the easiest way for me. So what I'm saying then, let's change that cosine squared into a 1 minus sine squared. So I have cosine t times 1 minus sine squared t plus sine t dt. And now this integral is ready for a single u substitution. So let's let u equal sine t, and then du is cosine t dt. All right, so doing that, we can finish this whole problem with a single substitution. Since I've done a u substitution, I do need to change my endpoints of integration. So here I have t equals 0 and t equals pi over 2. If I change that to u, sine of 0 is 0, and sine of pi over 2 is 1. And my cosine t dt, that's my du. And so what I have then is 1 minus u squared plus u du. And that's a pretty easy antiderivative. We get u minus u cubed over 3 plus u squared over 2. Evaluated our endpoints of 1 and 0. And that just gives us 1 minus a third plus 1/2. We can rewrite that in terms of sixths. So 6/6 minus 2/6 plus 3/6. And that should give us 7/6. And again, if you take a look at the solutions key, there's a different approach taken. There's also a very small error in one of the integrals at the very end. They get a slightly different fraction, but we've talked about this is the correct answer for problem 2. Okay, so I just want to rewind that problem for a minute and see if there's any questions. We started with a function given in terms of x, y, and z, and a helix that had parametric equations given for it. You might see some problems where you have to come up with the parametric equation. You might see some problems where you're given it. If it's a simple path like a line, right, that would be a problem where you could find the parametric equations. If it's something a little bit more complicated like this specific helix, then it's probably going to be provided for you. there might be some circular paths, right? Some problems where it's easy to find a parametric equation, but we've been given the helix here in parametric equations. So we're going to use cosine t for x, 2t for y, sine t for z. We do two things, right? R of t is that parametric equation. We're going to use r prime later, so we calculated r prime. We changed f of x comma y comma z to f of r of t. That is to say, we rewrote our function, which we can think of as a vector field, by the way, right? It's a vector valued function in terms of the parameter t. So that's what we did right here. We had to dot that with r prime. I did a little derivation of like where this formula comes from. This is really all you need to know for a problem like this. And again, this formula is also in section 16.2. So f of r of t, that's our parameterization of our function. We dotted that with r prime, which is the derivative of this helix here, times dt. Our dot product, right, which that's not just right multiplication, that's a dot product here. So we added the exponents, the x components multiplied together, the y components multiplied together, and the z components multiplied together. This is that moment where I told us to all pause. This is the choose your own adventure from here on out. Whoops, I missed my dt there. By the way, that's a t, not a plus. There. At this point, it's choose your own adventure for how you solve that that calc. Really calc 1 or calc 2 single variable integral. All right, so those are the problems that I wanted to take a look at. If anyone wants to go back and look at either of these problems, let me know. I'm also going to see if I can figure out how best to share files. Let's see here. Yeah, I don't see the file sharing option in the chat anymore. I'm going to guess. I don't know if you guys have seen, there's been some security concerns with Zoom. I'm not sure if we'll keep using it after this week, but people are crashing Zoom meetings and writing and doing some pretty awful things. They're working on ways to stop that. Password protecting meetings is one of them, but I think I'm unable to share files directly here. What I will do is I'll put these in a couple places. I think the best place for me to put these in D2L, there's a discussion forum. So if you click discussions, I've created a thread that just has information about my recitations. I've put the YouTube videos of past weeks in there. That would be a good place for me to post files where they're going to go out to everyone in the course, just people in sections 7 or 8. So I hope that works. So any questions on these line integral problems? Is it possible to list a brief step-by-step in words for these problems? Yeah, that's a good idea here. Let's see if I could write out a brief step-by-step for these line integrals here. Okay, so I guess maybe more so than a step-by-step, we should consider a strategy. Like, what's our general strategy for calculating line integrals? General strategy is, let's turn this into a single variable calculus problem by using parametric equations. Like, that's what we're trying to do. Depending on the problem, it's going to vary a little bit. So here's the first thing that I would say. Maybe it's an if-then statement. Do we have a parameterization of the path? Okay, that's the first thing. So in problem 1, they just said there's a straight line segment from this point to this other point. We have to generate the parametric equations for that path. In problem 2, where we had the helix, that was actually provided to us. So maybe I'll put this as a question, like, do we have parametric equation for the path? Okay, so we're going to call that R of t. Right, so that's our parameterization of the path. Okay, what are we going to do next? Well, let's rewrite f of x comma y comma z. Let's rewrite that in terms of that parameterization. So f of r of t. Right, so in doing so, we've converted from x's, y's, and z's to a function of t. Okay, so the other ingredient that we'll need then is r prime of t. Now, when I did the problems, as soon as I had r of t, I also calculated r prime of t. I knew I was going to need that a little bit later. And so, so what we did then is we took our integral along the path c of f dr, and we rewrote it in this manner. Right, again, that's dot product right there. These are both going to be vectors. Okay, and so if we've done steps 1, 2, and 3, when we rewrite our integral, right, this is an integral of multiple dimensions. This is an integral just with a single variable t. Right, so that was sort of our process through the problem here. Okay, so hopefully that's helpful there. I'll leave that up on the screen for a moment. Dan, did that answer your question? Okay, awesome. I will say this. So our book, there's certain sections that I find either annoying or sort of like impenetrable to just like open up and read. I think 16.1 and 16.2, they actually do a really good job of being gradual in their introduction through the problems. They take you sort of example through example. There are parts you can skip for sure, but I would recommend reading 16.1 and 16.2. They do examples in 16.2 just like the two problems that we did here, and they're pretty good at both comparing these problems in 2 dimensions to these problems in 3 dimensions and providing summaries and formulas along the way. Any other questions? So I'm gonna do the same thing on Thursday. I know some people came in after I'd sort of started with that example from Clinton and riding a bike in Livingston. I'll post that document to D2L. I think you did a really nice job with that metaphor. Feel free to also pop these questions into that discussion forum. Yeah, questions like, can you explain exactly what a line integral is? That might be a good one also for me to sort of think and write out a more detailed response to too. So I'm going to just pause, record.